The molecule, a physicist's perspective. 1. The molecule as a quantum system. For a physicist, a molecule is not balls and sticks. It is a many-body quantum system consisting of nuclei, protons plus neutrons, electrons, the electromagnetic field, and their interactions. The full problem is described by the Schrödinger equation for a system of n electrons and m nuclei. H cap psi equals E psi. The Hamiltonian includes kinetic energy of electrons, kinetic energy of nuclei, Coulomb attraction, electron-nucleus, electron-electron repulsion, nucleus-nucleus repulsion. A molecule is a stable bound quantum state of this system. 2. Why do atoms form molecules? The key principle is minimization of total energy. When two atoms approach each other, their electron clouds overlap. The system rearranges its probability distribution. If a lower energy stationary state appears, a bond forms. Physically, a bond is the formation of a stationary quantum state whose energy is lower than that of separated atoms. 3. Born-Oppenheimer approximation. The full solution is analytically impossible, but there is a powerful physical simplification. Nuclear mass is much greater than electron mass. Therefore, electrons move rapidly, nuclei move slowly. We separate motions. Psi of r, r approximately equals psi electrons of r, r times chi nuclei of r. First solve the electronic problem with fixed nuclei, then solve nuclear motion in the effective potential. This leads to the potential energy surface, PES. The minimum of this surface gives the equilibrium geometry of the molecule. 4. Potential well and bond energy. If we plot total energy as a function of interatomic distance, at large distances, energy equals separated atoms. At very short distances, strong repulsion. In between, a minimum. That minimum corresponds to the bond energy. The depth of the well determines bond strength, dissociation temperature, spectral properties. 5. Molecule as a quantum oscillator. Nuclei are not fixed, they vibrate around equilibrium. Near equilibrium, the potential can be approximated as V of R approximately equals 1/2 kx squared. This is a quantum harmonic oscillator. Energy levels are discrete. E sub n equals h bar omega times n plus 1/2. Even at n equals 0, there remains zero-point energy, a purely quantum effect. 6. Molecular rotation. A diatomic molecule behaves like a quantum rigid rotor. Energy levels, E sub j equals h bar squared over 2I times j plus 1, where I is the moment of inertia. Consequences, discrete rotational spectra, measurement of bond lengths via spectroscopy. 7. Electronic structure. Electrons occupy molecular orbitals, linear combination of atomic orbitals, LCAO. Psi equals C1 phi 1 plus C2 phi 2. This produces bonding orbitals, antibonding orbitals. If bonding states are more populated than antibonding, the molecule is stable. 8. Molecular spectra. For a physicist, a molecule is seen through its spectrum. 3 energy scales lead to transition type, range, physics, rotational, microwave, moment of inertia, vibrational, infrared, bond stiffness, electronic, UV/visible, electronic structure. Each molecule has a unique quantum fingerprint. 9. Molecule as a nonlinear dynamical system. In polyatomic molecules, vibrational modes interact, energy redistributes, nonlinear effects and chaos may appear. This is studied in molecular dynamics. 10. Statistical physics of molecules. Macroscopic properties emerge from molecular degrees of freedom. Partition function Z equals sum e to the minus ei over kT. From it, we derive heat capacity, pressure, and entropy. A molecule is an element of a statistical ensemble. 11. Molecules in quantum electrodynamics. At the fundamental level, interactions occur via photon exchange. Forces arise from U1 gauge symmetry. Chemical bonding is quantum electrodynamics in a complex many-body system. 12. Relativistic effects. In heavy atoms, inner electrons move near relativistic speeds. Relativistic corrections modify chemical behavior. Example, gold is yellow due to relativistic effects. 13. Molecule as an information structure. From the perspective of physics of information, a molecule is a configuration of quantum states, a stable form of energy and structure storage, in biology, a carrier of information, DNA. 14. Molecule between micro and macro worlds. A molecule lies at the boundary, too small for pure atomic physics, too large for classical mechanics. It is a regime where quantum mechanics dominates, complexity and collective behavior emerge. 15. Philosophical conclusion of a physicist. A molecule is not a thing in the classical sense, not a rigid object, but a stable solution of quantum field equations. It exists as a stationary configuration of electromagnetic interactions among multiple particles. All matter, life, stars, and planets are ensembles of such stable quantum configurations.